Okay, everybody, welcome back. And with all of these preliminary ideas in mind about our basic definition of what a logarithm is, it gives us an exponent, to which we raise the base b to get x. We want to go through and consider, well, what will our function look like? Well, there are a couple of options to deal with right here, but let's deal with the basic one right here. Let's deal with f of x equals logarithm base 2 of x. What should that graph look like? Well, if we do it out correctly right here, we're going to pick values of x and we're going to substitute them in for y. What kind of values of x can we pick? Well, certainly we can pick x equals 1. I'm giving you a few values right here. We could pick values of x like 1. Why? Well, because I know that y then would be equal to the logarithm base 2 of 1. And we're saying, okay, to what power must you raise the base 2 to get 1? Well, all right, well, 2 raised to the 0 we know is equal to 1, so that implies that y must be equal to 0 in this case, and so our graph must pass through the point 1, 0. Let's try a few others. What would happen if we take y equals the logarithm base 2 of 2? We're saying to what power y must we raise the base 2 in order to get 2? Well, in this case, our conclusion must be y would have to equal 1 for that to happen. So our graph must pass through the point 2, 1. Now, some of these other ones are actually kind of interesting. We might say, well, okay, y is equal to the logarithm base 2 of x equals 4. What happens at x equals 4? Well, we know what happens right there, because if we were to say, to what exponent must I raise the base 2 in order to get 4, the result is that our graph must pass through the point like y equals 2. Let's do one more. What happens at 16? Well, to what power must I raise the base 2 to get 16 is what I'm really asking right here. We're probably skipping over a few, but, well, what happens? Well, 2 raised to what power gives me 16? Answer, y is equal to 4 in this case, right? So we would actually use this expression right here, and let's move this down just a little bit here. We're saying when x is equal to 16, y is equal to 4. And there's a few other values. We could say, well, when x is equal to 8, y is equal to 3, because 2 to the third power is equal to 8. Are there other numbers that we could get? Well, sure. But let's take a look at these points that we have so far. Let's just check out what we have. We know this graph will pass to the point 1, 0. We know that this graph will be the kind of graph that will pass to the point 2, 1. That'll be the kind of graph that passes to the point 4, 2. As well as a point like 8, 3. You can almost follow the pattern right here. 16, we're going to get 4. So how should that look? Oh, let's try it out right here. Oops, am I missing something here? Looks like I am. Oh, I'm grabbing the wrong base. Hold on one moment right here. Let me correct that. Okay, so in my graph right here, y equals 2, well, I can see what's happening. It looks as though I'm actually getting values of x that follow along this pattern right here, but there's actually values between 1 and 0. What do I do about those? Well, there's definitely a point down here, right? Actually, this one's going to miss it right here, so it won't like those. But let's try it. If there's a point between 1 and 0, that means maybe 1/2 would work. Is there some value, x, that I can put into this function and get 1/2 as a result? That should be 1/2. Stand by for a second. So when we put in the number 1/2 in place of x, what are we really saying? We're saying, well, okay, to what power must I raise the base 2 to get the number 1/2? Right? So we're saying, okay, y is equal to some number that you would raise the base 2 in order to get 1/2. Well, what does that mean? We think, well, let's see, 2 raised to some power must give me 1 over 2, but I know that 1 over 2 is the result of raising 2 to the negative first, and therefore it implies that y must equal -1. And so this is the kind of graph that would have to pass through a point like 1/2 -1. And now we're starting to get an idea that, well, maybe this is a kind of graph that won't have any values of x that are less than 0. And so there are certain properties of these kind of graphs that we can always look at. For all basic logarithmic functions, the graph can be summarized with some of these following properties. First of all, the domain is all real numbers greater than 0. Now, if you want to contrast this to our exponential function, that's actually not a bad way to go, because if we say, let's look at y equals the logarithm base b of x, and compare it to the graph of y is equal to base b to the x, right? Our domain in this function was negative infinity to positive infinity, and that's now our range. And our domain of our logarithmic function was 0 to infinity, which was our range of our exponential function. And this makes perfect sense that these two functions are, in fact, inverses of one another. So on the exponential function, where we would have had a horizontal asymptote at 0, y equals 0, we now have a vertical asymptote at x equals 0. Instead of having a y-intercept at 0, 1, we now pass to the point 1, 0. So on our graph, we will have a point right here at 1, 0. We could say that our graph somewhere along the line here is going to pass through the point b, that's an x value, 1 for y, right? Let's contrast that over here, right? On our exponential function, it was the point 0, 1 before, and the point 1b over here. But not only that, because our graph of our exponential function might pass through a point like -1, 1 over b, our exponential graph will now pass through a point like 1 over b, comma, -1. And in fact, that gives us a few properties right here that we can always use with logarithms. Some really basic properties of logarithms that we'll use in the upcoming section as well. In fact, all of our upcoming sections where we need this go as follows. We say that, well, we always know that anytime we take the logarithm base b of 1, the result will be 0. We also know, as a rule, that anytime we take the logarithm base b of the base b, we get 1, because that base b raised to the first power is itself. And finally, we know that anytime we take the logarithm base b of the fraction 1 over b, we must get -1 as a result. Okay? There's a vertical asymptote here at x equals 0 in the most basic kind of graph, right? There's been no shift, no translation, anything like that. That's as opposed to a horizontal asymptote with our exponential function. So we have a pretty good idea of what's going to happen every single time we deal with an exponential graph, and we can use these properties to our advantage.